Okay. So let's start off with the example that we let you guys do last time. You guys got through that. What is the first step here?
Homogeneous.
Find the homogeneous how?
R squared plus 9. 0.
Plus or minus? 3i. So that means that your YH is going to be?
E to the, cosine 3t plus sine 3t.
Plus 3t. Right, and we can think of this guy, say, as the y1, doesn't really matter, but you can think of that guy as the y2. Okay. So those are our homogeneous solutions. Now, what else do we need to do?
Particular. We need to find a particular solution.
We do. How do we do that?
Y1 Wronskian integral.
So you find the Wronskian, which is going to be y1, y1 prime, y2, y2 prime. That's going to be cosine of 3t, derivative of that.
Negative 3 sine 3t.
And sine of 3t, derivative of that is 3 cosine 3t. That is going to be 3 cosine squared 3t plus 3 sine squared 3t, which is 3, that's just 3. So that is our Wronskian. And so now, we just find the particular solution by minus y1 times integral of y2 times g over w plus y2 times integral of y1 times g over w, where these functions do not go inside the integral, they are the coefficients. And so this would mean y1 minus cosine of 3t times the integral of y2 times the g, which is 2 secant 3t all over 3. Now technically this integral is a definite integral of some other limit, but whatever, we can ignore it. We're going to choose the constant of integration to be very convenient anyway. But don't think of moving this function inside here. The y2 sine of 3t times the integral of y1 cosine of 3t times 2 secant 3t all over 3. Now we're simply going to calculate that. So this is 1/3, factoring out the 1/3. This here, secant 3t is just 1 over cosine, right? So this is actually minus 2/3 by factoring out this 2. And I pretty much have the tangent of 3t. Plus, I can also factor out a 2/3 here. And secant of 3t is just 1 over cosine of 3t. That's going to cancel. So this is 1 dt. Integral tangent?
Natural log cosine 3t.
Huh?
Natural log cosine 3t.
Right, so that's cosine of 3t. Derivative of the tangent is the natural log of the, well, the negative cosine, right? Or you can do log of secant.
What's tan in terms of sine and cosine? Sine over cosine, right? So natural log cosine.
And do we need something else here?
Because there's a trick is natural log cosine. This is 1 over cosine.
We need to multiply by 1/3 because of the substitution, right? U equals 3t, g equals 3 dt, blah, blah, blah. And then plus, well, just integrate that with, that's t. So this is 2/3 t times sine of 3t. Of course, plus a constant, which we're going to ignore anyway. So, if this is be minus 2 over 9 cosine of 3t ln secant of 3t plus 2/3 2/3 t sine.
Oh,
So I'll take that to be my
there's a negative. So that means there must be a negative over here as well. I don't believe.
and so this implies general solution
Probably the outside is
is
positive.
going to be
The outside is negative.
the homogeneous solution
The outside is negative. Here it's
Plus-
negative 1. So
the particular solution. So that would be
3
minus 2/9
Yeah,
cosine of 3t and of secant of 3t.
Because there should be a negative here, right? Negative natural log. Okay.
Plus 2/3
Would you multiply the negatives? Would you use that inside?
Any questions on that one?
How do you know if, what part of the particular is a linear combination of the homogeneous? If it's not so obvious or immediate to you.
Oh, well, the thing is, it would be obvious because you would have, the only way to not, for different classes of functions, or you'd have to be a constant times one of the other ones. So this is not a constant times sine, it's actually a polynomial times sine, a non-constant polynomial. And this is a cosine times a logarithm. They're not going to be the same. Because if you take a constant times this plus a constant times that and set it equal to 0, the constants will have to be 0 for those guys. So pretty much the linear independence, when you have a very small number of functions, it's easy to check. It's easy to actually see that they're linearly independent. Because usually it just means neither one is a constant multiple of the other. So that's that problem. So there'll be a problem like that on the test on Wednesday. Another problem, in fact, that'll be on the test on Wednesday, which, if memory serves, we never actually did a specific example of it. I did a general example of it. That was when we had a repeated root, and I say, oh, we can use the reduction of order method to find that the second root has to just be t times the first root, if it comes from a second order linear differential equation with constant coefficients. What I want to do now is look at reduction of order more generally, a little bit more generally, as well as do it for a specific example. So, and say I never showed you. You also need to know that. So another example that you would need to know for the quiz, the test on Wednesday, is going to be, you should know how to do a reduction of order problem.
The question I had specifically was how do you prove the second is linearly independent from the first?
Oh, check, find the Wronskian, as long as the Wronskian is non-zero.
What would the other two, what would the g of t and 0 be?
Let's actually do it. I'm gonna do that.
Is that through Abel's theorem?
Hmm?
Is it through Abel's theorem, the Wronskian?
No, I'll just find the Wronskian.
Oh.
Because by the end of the process, you would already have the two solutions. You can just find the Wronskian for it.
My biggest issue of having with the reduction of order is organizing all of it. When you have all
Well,
this.
let's look at it. Let's get some tips. And that's going to come in handy with the topic that we're going to do tonight, because organizing is going to be a big issue.
It's
because things can get very long algebraically. Yeah, so that is going to be something. The idea is you're going to want to start to group things by like terms as quickly as possible is going to be the situation. So, reduction of order. So consider this differential equation. T squared y double prime minus 2ty prime plus minus 10y equals 0 for positive t. Assume y equals t to the fifth is a solution.
Exactly.
Find another solution. very handy technique. In fact, we kind of generalize reduction of order to figure out the formula for variation parameters. And we generalize reduction of order to figure out a lot of formulas, actually. It's a very useful technique. And we're lucky that it works out, but because of the existence and uniqueness theorem, if it works out, you can pretty much use it whenever it works out and not worry about it. So, you'll see a problem like this, as you would have seen in the review stuff that I gave you. By the way, the missing finals, I did upload them, so if you want to practice more finals, make sure you go back and check. No, on the math department on the math class webpage, right? So I told you to practice some funds from a bunch of finals, but when you go to the main page, those finals weren't there anymore. I dug them up. So I had downloaded them way like 5 years ago, the first time I taught the class. Oh, hey, I found them in an old folder and I uploaded them to my page, so you can go there and you can practice some more. As well as I uploaded my first 2 tests from the last time I taught, so with the solutions. So of course, don't look at the solutions first. Try to go through the test, time yourself, see how well you do afterwards, and try to fill in your gaps afterwards.
Should we give a look for the other problems that you said not to look, to like not do, or because you said to do only like specific problems for those 2 past exams?
Yeah.
So don't look at the rest.
I wouldn't. It would be a waste of time. So like even for test 2, like mechanical vibrations, I'm definitely not asking you about that. So if you look that up, that's
Even as a bonus?
no, even as a bonus, I wouldn't ask it. It's too many sections away. That's like 2 sections away.
What about Bernoulli equations?
What about
Yes. We did it.
I think I did one, but
You did.
Yeah,
I'm
you
saying
did
about the
one.
test, like, should we be?
yeah, you should know what you mean. I also, in addition to all this, I uploaded a mock test. So you probably should look at that one as well. So that one I uploaded like yesterday or the day before, I forgot. So your test would actually look more like that one the most. But I didn't post solutions for it, I just posted some prompts, like, it'll look like this. Okay, there's also going to be a problem like this one. So you're going to have a differential equation. I'm going to tell you one solution, and you will find a second solution by reduction of order. We already know for a second order linear differential equation, there are only 2 linearly independent solutions, so that will allow us to find the general solution here. So let me actually add that just because of the question earlier. So hence, find the general solution and show the solutions are linearly independent. So let's add that there.
I have a question.
Yeah.
Don't you have to use the uniqueness theorem to show that this satisfies some condition where it only has 2 solutions and not more than 2 or less than 2? The existence of uniqueness theorem?
You could state that. I don't think I asked a question where that would be the case though. But the idea would be, if I divide through by the t squared, this will have a unique solution on any interval where the coefficients are continuous. So here I have a 1 over t, here I have a 10 over t squared. So as long as my t is non-zero, I'm on an interval that does not include the origin, then I would have a unique solution that has 2 pieces to it on that interval. So let's actually do that. So how does reduction of order work? Well, you assume the second solution is some function times the first solution. So if I call this guy one solution, we're going to assume y2 is some function which we usually denote by v times y1. I'm just going to call this v y1 so I don't have to write down a lot of stuff. But whenever I write v, it's a function of t. So what we're going to do is we're going to find all the derivatives, we're going to plug that into that guy. So this means y2 prime is going to be product rule.
V prime y.
So this is going to actually plug this guy in. So this is v times t to the 5th. So it's going to be v prime times t to the 5th plus v times 5t to the 4th.
Second.
And then, so here's where you can kind of start to slow things, compress things. So here, notice that if I were to do this, you'd have to kind of do the product rule twice. I mean, at this point, I think that's okay. I would actually not worry about it right here. So if I do the product rule twice,
V double prime t to the fifth plus v prime 5 t to the fifth plus prime v t to the fourth plus
20 v
5
t.
now I'm literally going to plug that all in. So here I would start to clean things up. Once I have several terms with like a v prime, ultimately the v's are the guys I'm going to want to group. So I'd probably start grouping these guys. So this is going to be v double prime t to the fifth plus I would have v prime times 5t to the fourth plus, that's just 10t to the fourth. Plus 20v cubed. I'm going to multiply all of this guy by t squared. So I'm going to have v double prime t to the 7 plus v prime 10 t to the 6 plus 20v t to the 5th. Okay, or what?
t to the third. Why? Times y to t squared.
T squared. Yeah, multiply by t squared, so the 5th becomes 7, this becomes 6, this becomes 5th. Yeah, that's right. What's wrong? What's wrong?
Nothing.
I don't like mumbling though, but I don't understand what the problem is. Okay, so now I'm going to take minus 2t, multiply by this guy. One way you can actually do that is to line things up. So notice that if I take minus 2t times this, I would get minus 2 this to the 6. I can put that right under here. And if I multiply this, that's going to be minus 10 vt to the 5th. Then I'm going to multiply the first one by minus 10, just minus 10 times that. And that is going to be,
I see.
and all of this is equal to 0. So what's going to happen now is, notice that this is 20 vt to the 5th minus 10 minus 10, so that's going to die. I'm going to have here 10t to the 6th v prime minus 2t to the 6th v prime, so this is going to be 8t to the 6th v prime, and that's just going to be v double prime t to the 7th. Now notice here my t is non-zero, so I can divide 2 by it. In fact, I can divide 2 by t to the 7th. This will be v double prime plus 8 over t v prime equals 0. So that all collapses to that. Now what you're going to notice is that only 2 v's remain, and they differ by 1 derivative. And that allows me now to do what we call reduce the order, reduction of order. Basically, you reduce the order by doing a substitution.
Yeah, using
Right, so
is there a
here,
different name for this? Because it sounds like we're doing a reduction of order, which is a different thing inside another reduction. Is there a different name for like sending w to v prime and w prime to v prime?
well, substitution is the general method. Yeah, this falls under the umbrella of substitution. But applying substitution in this particular case, what it turns out to be doing is if I say u equals v prime, what ends up happening is I end up with u prime plus 8 over t u equals 0. So I go from a second order situation to a first order situation. So this particular substitution reduces the order. So that's just a first order differential equation. So we know that we can multiply through, well, this one is actually separable, so it's even easier to do. So du over du over u is going to be equal to minus 8 over t dt. Right, subtract this and then divide by the u. Then I can integrate both sides. So it's going to be ln of u is going to be equal to minus 8 ln of t plus a constant. Technically, I don't need the absolute values here because the t is positive, but let's just leave it in case. Now you can e both sides. Your u is going to be equal to some constant e to the minus 8 ln of t, which is just going to be some constant times, well, t to the minus 8. Right? Bring this up, e and ln would cancel, I just get t to the minus 8. The t is positive, this was assumed in the very beginning, so I can drop the absolute values without consequence. So I get u equals that. But that means that my v prime is equal to this.
So that would be dt.
Yes?
It's all in the top. Where'd you get minus v prime 2t to the power 6?
From the first derivative, it was minus 2ty prime. So I take minus 2t times that, I would get minus 2t to the 6t prime. Take minus 2t times the 5vt to the 4th, and I get minus 10vt to the 5th. So where these guys are coming from. This guy, this line here, is coming from the t squared y double prime. This line here is coming from the minus 2t y prime. And this line here is coming from the minus 10y. Where my y is v times, where my y is v times t to the 5th. So if I multiply that by minus 10, I just get that. My y prime is this. If I multiply by minus 2t, I get this. And my y double prime is this guy under here. So if I multiply that by t squared, I get the top one. So then when I add all these guys together, they add to 0, and then this side simplifies to that. Then doing the substitution reduces the order. It's a first order differential equation. In fact, this one is separable, so that's really nice. And now I get here, and at this point, I can now integrate both sides again. So this means that your v is going to be equal to I1 to the power, divided by the new power, divided by the minus 7 is going to give us some other constant, so I can keep that plus another constant v. So this means that my y2 is going to be the v times the y1, where y1 is t to the 5th. So that's c t to the minus 7 plus v. And so this is going to be c t to the minus 2 plus d t to the 5th. Ignore because redundant, because it's a t to the 5th, which is already the first solution. So it turns out that this guy is your second solution.
When you integrate CT to negative, are you supposed to divide it by?
Yes, so technically I'm supposed to divide this by a minus 7, but it's still just another constant. I'm not too worried about it.
I always assess it.
Yeah, I mean, yeah, it's kind of confusing. It's for the first time, like a math class is really starting to feel like a physics class. I ain't got to worry about it. The cow's a sphere. Don't worry about it. We're in a frictionless surface. Don't worry about it. Yeah, but that's that. Yeah, we're kind of
The C's
have
make
that
me very
attitude.
uncomfortable.
What?
The C's make me very uncomfortable.
I mean, you can do it if you want to do like a C1 and a C2 and then.
I was thinking with the greatest decisions. Like, no,
Say
I don't care, I get scared.
Yeah. Anyway, so this means the second solution is the second solution. By the way, for a problem like this one specifically, we are going to show how to find it using another method. Euler's, we're going to look at it as something called an Euler's differential equation. That's way in another chapter though. That's chapter, I want to say 5. Anyway, so this also means the general solution is going to look like y equals c1 times the original, which is t to the 5th, plus c2 times t to the minus 2. That would be the general solution. Now, how would you show that these are linearly independent?
Figure out what the y's are in C1 t to the 5th and C2
Just
t
do
to
the
the
ones.
negative 2. Take the derivatives of each of them and then find the Wronskian.
To check linearly independence.
Oh, it has to not be 0.
Linear independence, we must have the Wronskian non 0. So that must mean, if I look at this Wronskian, that's going to be t to the 5th, the derivative of that is 5t to the 4th. Look at this guy, this is t to the minus 2, derivative of that is minus 2, t to the minus 3. That is going to be minus 2t squared minus 5t squared. And that is going to be minus 10t squared with t greater than 0. So
minus 7.
Minus 7. T squared with t greater than 0. This means that the Wronskian is non-zero. And that means they're linearly independent.
T's a fifth for y2.
That's the y1.
No, at the top. What about y2 is?
This?
Yeah.
Oh, because y2 was assumed to be v times y1. Remember? That was an assumption from the very beginning. We said y2 is some function times y1. The y1 is the t to the 5th, and this is the function v. So I just plug it back into that. V equals this. My y2 is this times the y1. So the second solution is t to the minus 2. That makes this the general solution. I can check that it's a fundamental set of solutions because on the required interval, t is greater than 0, the Wronskian is non-zero. In fact, the Wronskian is always negative on that interval. So that's another kind of a specific situation for reduction of order.
So putting it into like the semi-matrix format is going to be our best bet for seeing where we get sub-canceling out, right?
Yeah, you can just line up the like terms. It'll be easier to see.
It's so easy to get lost during it. That's my biggest issue.
Yeah.
I understand what to do, but I'll...
Granted.
Yeah.
It's par for the course.
So if we didn't have the t is greater than 0 condition, would that Wronskian not be sufficient?
You would have to make a clause. You'd have to say something, like if you weren't guaranteed this, you'd have to state, we only have linear independence on intervals where the origin is not included. You have to say that as a sentence.
Okay.
So as long as t is non-zero, we are fine. We can have these two linearly independent solutions and give them a unique general solution. Unique particular solution.
That initial condition, though, is kind of guaranteeing that the only way that we would get 0 is if the two terms cancel out, right?
Yeah, in fact, the only way you kind of get 0 categorically is if one is a constant times the other. Okay, so that's that.
Yeah.
Let's actually talk about another way to get a particular function. So assuming you get through all the review materials, you studied and you're like, you feel over-prepared, like a friend over here. you might want to shout out bonus problems. Here is a bonus problem type that I'm going to be putting on the test. It's called Undetermined Coefficients.
This is the one you read in the one that's in the picture of that was like this one.
But up until now, it's not bonus, like
Huh?
the actual test, right? Up until now, it's.
Yeah, so what we ended is the test, right? This is the next topic, so you can see this as a bonus problem. So if you're like, you don't care about the bonus problems, you can not half pay attention or just, or decide to pay attention after Wednesday. But yeah, a problem like this will be in the bonus section. And in the grand scheme of things, it's not that bad. So if you actually finish everything else, you might as well learn. It's not Once you memorize the first steps, which you can memorize in 20 minutes less. Okay, so this is an alternative to find yp. However, it's not as general as variation of parameters. It works in very specific situations. Do I want to tell you what those situations are, or let that one first?
Yes.
Tell us.
I guess I'll tell you what the situations are. And then I'll explain like why you care, but you don't need to know why technically. These are. Okay, so in the below, I'm going to push this up, it's going to be below. Below, I'm going to use several notations. Q sub n of t, whenever you see that in what I'm about to write down, this just means a specific nth degree polynomial. Given as, this should be interpreted as the general nth degree polynomial. And I think the rest will be self-explanatory. I mean, I can say here, t to the k. This I'll explain more when we're doing examples. This will become more clear. This is the smallest power of t that ensures yp is linearly independent of yh. Okay. Now, that being said, so that's kind of the setup. Let me just give you the data and then maybe explain a little bit. So the idea here is we can use this method whenever the g of t is self-similar to itself upon repeated differentiation. And not all functions behave like that. Exponential functions behave like that, for example. Polynomials behave like that. Derivative of a polynomial is a polynomial. If you look at the trig functions sine and cosine, derivatives of sines and cosines are just more sines and cosines. If you look at a polynomial times an exponential, the derivative is just a polynomial times an exponential, etc. So we're looking at functions that are self-similar. So here is the situation. So in, say, y double prime plus p of t, y prime plus p of t. It actually works higher for second order, actually. Equals g of t. So here's the situation. There are two things you kind of have to pay attention to. There is the actual form of the g of t. And then there's going to be the form that you're going to choose for the YP. So, you have some random second order differential equation. Suppose your g of t, what that looks like, is some specific nth degree polynomial. So for example, you can have g of t equals, say, t cubed plus 1, right? So you have a second order differential equation. On the other side, you see t cubed plus 1. Then the form that you would pick for the yp is p of n of t. So for example, this is some specific third degree polynomial. You are going to write down for your yp the general third degree polynomial, which is going to look like a t cubed plus b t squared plus c t plus 1. Right? You account for all terms and you make these arbitrary coefficients. Right? Now, in the beginning, you don't know what these coefficients are, hence the name undetermined coefficients, right? You're going to guess that's what your particular solution looks like, just a generalized version of the g of t. Now, at the end of the day, you also don't want it to overlap with the homogeneous, so you are going to multiply by t to the k. And we'll talk about what that actually means pretty soon. I'll show you 3 examples of what that means. So that's one situation. You can keep adding this to the table, I'm just running out of space. So this would be the next row of the table. So suppose your g of t looks like this. It could be some specific polynomial times an exponential. Say e to the at. Whenever you see that, the form you're going to guess for yp is going to be the general nth degree polynomial times e to the at times a t to the k, which is going to be the smallest power of k to create linearly independence. So, for example, if you look on the right side, by the way, you should have the t to the k. So, for example, if you look on the right side and you see something like t squared e to the 2t, what would you guess that your particular solution looks like? Well, the general second degree polynomial times e to the 2t times t to the k. Okay, we're going to look at the t to the k more specifically soon. Like, you have to know what the homogeneous solution is to know what the t to the k is going to be, right? So just like how when we had repeated roots, if we had like one solution was e to the 2t, what do we choose for the second solution? t e to the 2t, right? Well, if you know that one solution is t e to the 2t, what would you choose for the second solution? You'd actually multiply by t again. If the other guy is t squared, what would you choose? t cubed. Right? You keep multiplying by t however many times you have to do so that there's no overlap with the homogeneous. So it depends on what the homogeneous is going to look like. But
You know, can the k be negative?
no, it's always going to be some positive integer.
How do you know that?
That can be determined once you have the homogeneous solution. So the point is not to be like the homogeneous. You don't want any part of your particular to be a constant times any part of your homogeneous. That's the idea. Another form, if you look on the right side, and it looks like some polynomial times, actually it could be either a sine of at or a cosine of at. The form of your yp. Now sine and cosine, these guys are, I won't say somewhat strange, but you have to be aware, if any one of them show up, both of them are going to show up for your particular. So you will assume a solution looks like the general nth degree polynomial times the cosine plus another general nth degree, well, you can put it all in one actually. you're going to put a sum of sines and cosines times UTK. And why is that? Because let's say your g of t is a cosine. The second derivative is going to be another cosine, but the first derivative is going to be a sine. So if your g of t, if you assume your solution looks like a cosine, you'll have both sines and cosines in the derivatives. So once any one of these show up, you always assume that the most general form is going to have both of them. So for example, if you look on the right side and your g of t looks like t cubed, say sine of 5t, then what you're going to do is you're going to look like at cubed plus bt squared plus ct plus d times sine of 5t. So it's going to be that polynomial times the cosine plus that polynomial times the sine, and of course you are going to multiply by whatever you need to, so that none of these guys overlap with any part of your homogeneous. And of course you can have like literally all three all at once, but that's kind of the last situation. So you could have something that looks like this. So it's pretty much polynomials, exponentials, sines, and cosines, or any product of these. You'd be able to, where only one trig function shows up. This is very specific situations. So q of n of t times e to the at times sine of bt or cosine of bt. Then you have a general nth degree polynomial times the e to the at sine et plus another general nth degree polynomial e to the at cosine et
T of k.
times t of k.
You could write it there.
This should be here. And those are all the situations. So undetermined coefficients work specifically for if the right side is a polynomial, or a polynomial times an exponential, or a polynomial times a sine, or a polynomial times a cosine, or a polynomial times an exponential times a sine, or a polynomial times an exponential times a cosine. In any other situation, it's not going to work.
Why would you use this over variation of parameters?
I don't know what you want to use it for. But it's quite popular. Because they're, I don't know why I use this.
Wait, then why are we learning it? If it's like redundant.
Really, the only reason I teach you this is because engineers like it, but math people will be like, why would you do that? Like I have a general form that will work with any case. Like why would I want to know an extra thing? We're learning this hit, basically, that's the idea. So you can talk to your engineer buddies, yeah, I did undetermined coefficients, yeah, I did 1, 2, you're over the beers and But that's why we're doing it. So. Yeah, but your life would be much different if you never learned this.
Wait, so could we solve the bonus with only the variation of parameters?
Huh?
Could we solve the bonus with only variation of parameters?
In any situation where undetermined coefficients would work, variation of parameters will also work. But it doesn't work the other way around.
Oh.
Variation parameters can deal with things that this can't. So for example, in the example that we started the class with where there was a secant, can't do this with a secant.
We write as 1 over cosine.
Yeah, it's still not going to work. Because when you differentiate a secant, what happens? You get a secant tangent.
That's still a trigonometric set.
Yeah, but it's not a self-similar trigonometric thing. Like it doesn't look like itself when you differentiate it. Right? Sines and cosines end up looking like themselves when you differentiate them.
I mean, how does a sine look like a cosine? What constitutes as looking like it? This means like it's within the vector space, right?
Yes.
So with trigonometric identity, also do in the vector space, like
Sines and cosines give other sines and cosines. If I take a sine and I keep differentiating forever, nothing is going to show up besides sines and cosines. If I take a secant and I start differentiating forever, I'm going to have tangents popping up, I'm going to have different powers of tangents and different powers of secants popping up. So the first derivative is going to give me a secant times a tangent. Then after that, I'm going to have to do a product rule. That's going to be a secant tangent squared plus a secant cube. So now there's a secant cube showing up, and a secant and a tangent squared times a secant. Like, none of them are going to look the same. But if I start off with an e to the 3t, keep differentiating that, I'm always going to get a constant times e to the 3t ad infinitum. Right? Take a sine or a cosine, I'm always going to get sines and cosines ad infinitum. Like, they are self-similar in that sense. And not many functions are self-similar upon differentiation.
That's the technical term for it, for when you cycle like that, self-similar?
That's what I call it.
Alright, I thought that too.
Okay, so now, that's the table. So this is what you would choose for your YP. Okay. So now, let's talk about the process. It also works for higher order linear ODEs, which you might call folding. But let's keep it specific to second order. So given y prime plus qt y prime plus qt y equals g of t, where g of t is of one of the forms in the left column of the above table. We will choose a form YP that looks like G of T, right? So the idea is, if I have a bunch of, the left side is going to be me taking some function and doing a bunch of derivatives with it, and it's giving me some other function. If I make the assumption that the function itself is self-similar upon repeating differentiation, then the left side of here giving me something like the right side is going to make sense, right? So if I say, oh, this is e to the 3t, then it makes sense to assume that all these functions are a bunch of e to the 3t's. So that when I differentiate them and add them together, I get some other e to the 3t, right? I can't make that assumption if this is a secant, because it could be whatever and I get a secant at the end, right? So now we can have, so I want to choose my particular solution to look like the g of t. So here we're assuming y is self-similar upon differentiation, which means it has to be one of those forms. But, and this is a big but, we want, I like big buts, but we want YP to not look want it to look like the homogeneous solution. Why? Because if my particular solution is the homogeneous solution, if I plug it in, I'm just going to get 0 equals 0, which is useless at best. And so I want it to look like the GFT, but at the same time not really look like the YH. To prevent the latter multiplying by an appropriate power of t. The smallest part you need to make them not look like each other. So yeah, so lastly, this will give a YP with undetermined coefficients. To determine them, what are we going to do? Well, if it solves a differential equation, we're going to take a bunch of derivatives, plug back to the differential equation, set up a system of equations, solve for the coefficients. We can determine them if required. Sometimes I'll actually tell you, just tell me what the form of the particular solution is, don't tell me what the ABCs are, I don't care. So if required, you need to find them. We can, by plugging in YP into the ODE and solving for the coefficients by a system of equations.
What do you mean by system of equations? Like,
Let me show you what I mean with examples. So, let us actually jump into an example because otherwise this is going to be somewhat confusing. Let's see, where did I have it? Be very confusing.
Yes.
Well, I'm very confused. I don't know if I speak for everybody. Okay.
How is it possible that math majors do not have to take this class? How is it possible that math majors don't?
Because they literally expect you to pick it up on your own. Like you're going to go into classes and they're going to assume that you know everything about differential equations. It's the kind of thing that they expect you to, just spend 2 weeks in your summer and read up on.
They make a specific whole class and have to solve these things and then they just assume.
Yeah, because it's not a theory-based class, so math people usually don't really care. Wow,
Yeah,
look at those
it's true.
examples.
I'm not a math major.
That's
It's useful though.
Oh, differential equations is incredibly useful.
Yeah.
But again, a class at this level, they're not gonna, they expect you, they don't really. A bunch of examples, I don't know where I put them.
there's an example in your bonus second text. I'm going to see this with you.
Yeah, but I literally wrote down like 12 of them. We were just gonna go and like really just kill it.
Do you find chalk on all your things, Jhevon?
Yeah, chalk is always a
it's one of those studies, you know,
Why
like 5
this
participants
page
and
is out of place?
0.649 or 0.51, and they're like, oh my god.
Yeah, so I have examples A through K. Let's do it.
Wait, how fast can you do
So we're going to do it simple. We're not going to worry about the arbitrary constants for the now. Find the YP by undetermined coefficients. Do not find the arbitrary constants. So let's do several. So 8y double prime plus 4y prime plus 3y equals e to the minus e to the t. E y double prime plus 4y prime plus 3y equals e to the minus t.
derivation of parameters? What ODE do you think you're going to get?
Let's do those.
Something they're like purposely set to
T by
throw, set up like
A.
that.
So, first thing you want to do, remember you want it to look like the g, which in this case the g is e to the t. But you do not want it to look like the homogeneous, which means you first need to find the homogeneous to make sure that you're not overlapping with any of it. So
r squared plus 4.
So plus 3 plus 1 equals 0, so r is equal to minus 3, r is equal to minus 1, so your y is going to be c1 e to the minus 3t plus c2 e to the minus t. So now you would choose your yp to be
T to the
T to the 1?
T to the 1, I was going to say that, but I don't know what's right.
Why not T to the 0?
So first, we want it to look like the g. So the g is a constant times e to the t. This is a specific 0-degree polynomial times the exponential. So I'm going to start out by putting a general 0-degree polynomial times the exponential. Now I'm going to check, does this overlap with any of these? The answer is no. Done. Okay, so first make it look like the g, then check. Any overlap? If none, you stop. If yes, multiply by t.
Overlap would mean that it becomes.
One is a constant times the other. This part B has an overlap.
Okay, let me see.
So
Wait, could you set k, t to the k or k is equal to -2 because it's less than 0?
you wouldn't. K is always going to be a positive integer.
You really want to make it negative.
Yes.
I don't know. You just like So same guy. So I know what YH is. This is C1 e to the minus 3t plus C2 e to the minus t.
Ah, that's the overlap.
So now I'm going to say choose my YP to be equal to, well, my G of t is just a 0-degree polynomial times that exponential. So I'm going to put a general 0-degree polynomial times that exponential. Then I check any overlaps. Well, yes, there is. This is a constant times e to the minus t, and that's a constant times e to the minus t.
Oh.
Wow.
8. 8.
And that works by reduction of order, but we just know that it's going to work out by reduction of order, so we just multiply by t.
I'm sorry, what is the other t?
All that explanation is.
Without the t,
Yeah,
this looks just like that.
okay.
That's a constant times e to the minus t. This was a constant times e to the minus
So we
t.
just multiply by t to the first.
Which means these two are not linearly independent. Which means if I just chose this as my yp, that's a homogeneous solution. That's not going to solve the non-homogeneous solution. So in order to make sure it's going to solve the other one, multiply by t. it is now going to not be a homogeneous solution. And it will be linearly independent to the homogeneous solution. C.
Any t times a constant. That's our.
Okay, try these girls. You guys try this. C, y double prime plus y equals x e to the x. So that's an x there. Y double prime plus y equals 3 sine of x. Y double prime minus 2y prime plus y equals e to the t. Y double prime minus 2y prime plus y equals t to the t. Now, yes, so far I realize that you might say, oh, this must be why people do undetermined coefficients instead of variation parameters, because that was easy. Like, we haven't started the problem here, right? In general, you have to find the A, but here I just want you to get used to actually picking what the form would look like. So the problem actually hasn't even started yet. Finding the A is what's going to be annoying. Finding the A, B, and C, and all that stuff. So, all right, tell me what you're thinking for this one.
It would be a first degree.
Cosine.
No, but before we do anything, we need to know the homogeneous, because we need to not overlap.
Oh, it's
Cosine
a
B.
solution.
So that's
C1 cosine
C1 cosine of x plus C2 sine of x. Okay, so now that I know that, I can know for sure that I'm not going to overlap. So, what I do is I look now at the g of t. What's the most general form of this?
AX plus B.
Ax plus b
E
times e to the x. Now I look. Do any of these guys overlap with any of those guys? No, those are trig functions. That's an exponential.
Wait, I have a question.
Yes.
Did you say you could rewrite e to the x in cosine x plus I sine x?
No, we can write e to the ix
Yeah.
times as
But isn't I
cosine.
just a constant, so wouldn't that be inside the...
Yes, but different constants aren't the same. If you have e to the at is linearly independent e to the bt if a is not equal to b. That's true.
But they're both
It doesn't matter. Find the Wronskian of that. It's not zero.
Quick question.
Yeah.
What A came from, where did plus B come from?
This is a first degree polynomial times the exponential. We want to write down the general first degree polynomial times the exponential. This is like your q sub n. This is like your p sub n from the previous table. Okay, so we have this. I already know that the y homogeneous is the cosine x plus c2 sine x. So my yp, what is that going to look like? Well, this is a 0 degree polynomial times sine. You must put a sine x plus b cosine x. Whenever either a sine or a cosine shows up, you put both. Now what we're going to do is we're going to look, do any of these guys overlap with any of those guys? Yes.
Yes.
This guy overlaps with that guy. So, in order to prevent that overlap,
They both overlap?
I'm going to multiply this by x.
Oh, yeah, right.
And I only need x to the 1, right? I don't need to go further than that. Let's do it again. By the time we get to I, everyone's going to know what I thought. So I have tons of these examples.
It just feels like adding on to like 3.1 to 3.5, which is makes sense in the second section.
Okay, someone come at me.
Our
First step. R squared.
2r plus 1. That's r minus 1 r squared.
So at repeated root, what's our homogeneous?
C1 e to the t y, sorry, e to the t plus C2 p e to the t. And particular-
So now if I choose a YP,
That's a e to the t times t to the k because they overlap.
right, so I multiply by T because it overlaps with that one.
Now t squared.
But now it overlaps with that one.
Oh,
Do it again.
got me.
That's the K, right? That's what it means to the T to the K. The smallest power you need to not have an overlap. So if you multiply by a T and you realize, oh, it still overlaps with someone else, do it again.
What about t to the 2.1? That's not the smallest power.
What? T to the square, the smallest
1.9
integer.
recurring.
We're gonna do
Integers only.
1.2 power.
It's like this.
That's horrible. It's t to the 1.2 power.
Actually, that's the integer though.
Doesn't have to be.
Just add it
You
to
see
the
this is 1.9. That's still 2.
Okay, so you have this. What would this end up looking like? So it's the first, it's the same left side as that. So you know your YH is going to be the same thing. C1 e to the t plus C2 t e to the t. Which means if I want my YP, what does it look like?
AT plus B.
AT plus B times the e to the t. That's the general form. Now,
Yeah, it's fine, I think. Oh, no, it's not fine.
it's not. If I multiply that out, it's literally that guy.
Yeah.
What about T? Where?
Yeah, it's 1t.
So what would happen if I multiply by t?
Still have one.
You still have one, yeah.
Why not?
One thing would still overlap. The t times the b e to the t, right? If I expand this, I get a b t e to the t, which overlaps with that. So I multiply again.
Sits
Is there any overlap?
No.
No, that's a t cubed e to the t. This is a t squared e to the t. It doesn't overlap.
I mean, to be sure, wait, the t has to be the smallest, right? Or it could be, this is what I say, what if we just do t to the fifth and just, you know, you
call
Yeah,
it.
but why would you do that?
just.
You have to be sure that there's no.
Like
Sorry.
That's what I'm saying.
So here's how real life works. There are always limited resources. You have to understand, even when you're using a computer, every bit of information that you don't need, if that computer is running billions of operation, it all adds up, right? You just using an extra third power, it's just an extra third power. Trust me. You run that through a computer billions of times, it starts to add up. It starts to slow down your hardware. It starts to take too long to compute. You always want to be as efficient as possible.
But this case is kind of different.
Right, so for you, it's just scribbling a number on a page, but
Yeah,
if it's an actual big problem that you're going to feed into something to calculate.
Have you ever crashed a mill lab?
What?
Have you ever crashed a mill lab?
No.
I've made it go really slow before.
Oh,
Well, I like.
the blacklist
I crashed
IP, that's it.
Wolfram
No
before. I
more
don't use
questions.
Wolfram.
The blacklist IP, that's it.
Wolfram just-
Yeah, no, please, no more.
Wolfram is just like, ran out of computation time. You ever got that from Wolfram?
No, I've never got that one.
I've gotten that from Wolfram. Yeah. Probably because I chose a T to the fifth when I should have given it
Did you do one of the equations now? The,
So some things it's surprised. You'd be surprised. Like, you have to understand that it's very easy to go from a doable situation to a non-doable. Like that, fine, no problem. Impossible. You know what I mean? Like, keep things as small as possible because you never know when you just decide to, oh, let's just bump it up an extra power. No, it's not how life works. You want to keep it as small as possible. Let me just copy these down, you guys can practice, and we will finish them on Monday. So, how many did I do? F. Okay, so here's a G. H. challenge problem. Because technically we haven't dealt with this yet, but what if, how do you think I would deal with a fourth order differential equation? And I mean, after today's class, you can go home and look at the solution to the bonus problem on the thing, on the review test, and you can actually see if you can actually figure out how I came up with the answer.
So how did you?
That's on the boat.
So bring this problem to its complete. Which means find all the arbitrary constants, actually find the function that solves this. If you haven't finished studying for the test, I would not go and do these. Go study for the test first. If you have extra time on your hands, then you can go over those.
Yeah, I have a question.
Yeah.
With the variation of parameters, without the given conditions, you could always find the undetermined coefficients, right?
Without what?
If you use variation of parameters, there would be less unknown coefficients, so C1, C2. But if you use the...
Yeah, you wouldn't have any, you'd only have the C1, C2 unknowns that you can find from here. But with undetermined coefficients, you have the C1, the C2, and the ABCs. So you have more coefficients to work. Yeah.
So I think we have a question where it's like, we just let in with
Yeah, you're going to find a bunch of derivatives, you're going to plug them back into the equation, and then you're going to solve for the coefficients by equating